Much of what constitutes rational economic decision-making relies on knowing exactly the choices that we're making and the trade-offs we have to consider. But in many instances, these can't be known with certainty. We often have to make decisions without knowing the outcome beforehand. In this chapter, we'll start looking at risk and uncertainty and how they will impact our decision-making. For this class, we're going to skip a detailed treatment of probability theory, and we're just going to describe a random variable, x, as something that can take on a number of different values. So, for example, we can think about a dice roll or a coin flip, or something like, what's the temperature going to be tomorrow? So I can think about a discrete random variable, like for a dice roll, the outcome can be 1, 2, 3, 4, 5, or 6. So there's a finite number of values that it can take, or I can think about a continuous random variable, a random value that's between 0 and 1. The probability density function, or the PDF, is going to describe the probability that x takes on each of its possible values. And I say describes the probability because this is not the same as saying that f of x is the probability of that particular value occurring. So if I have a discrete random variable, then fxi is indeed the probability that x equals xi. So for something like this, a dice roll, the probability of each of these outcomes occurring is 1/6. So the density function will be equal to 1/6 at each of these values. But this is not going to be true for a continuous random variable, because if I look at a continuous random variable like this x here, x can take on any value between 0 and 1. So there's an infinite number of values it can take. And the probability that it takes on each of these values is 0. So the density function is not going to give us the probability that it takes on each specific value, but it will describe it. How? If I integrate the density function between a and b, that's going to give me the probability that x falls between a and b. We can use the probability density function to compute the expected value or the mean. So for a discrete random variable, I would sum up over all the possible values. I would sum up x times density. So this would just be the average value that x would take. For a continuous random variable, I would integrate x times f of x dx from minus infinity to infinity. So along the entire range of values that x could potentially take. The variance of a random variable is going to tell us how spread out the values are. So we can define the variance of a random variable as the expected value of the squared deviation from its mean. So the expected value of x minus the expected value of x squared. The standard deviation of x, or sigma x, is equal to the square root of the variance. And it's usually easier to interpret the standard deviation because the standard deviation is going to be in the same units as the variable itself, whereas the variance will not. We can say that a gamble is fair if the expected value is equal to 0. So this would represent some bet where if you kept playing, then on average, you wouldn't win or lose. It would be neutral on average. So, for example, you could have a coin flip where on heads, so with probability 1/2, you would win $100 and on tails, you would lose $100. Now, we commonly observe that people would reject fair gambles like this. So if you are offered this particular bet, most people would decline. This tells us that people are generally going to be risk averse. So they don't want to take on risks unless there's some kind of gain, right? So here, there's no gain on average. If I was a risk averse person, I would want this prize to be a little bit higher before I'm willing to play. Now, of course, this doesn't describe everyone. Some people are risk loving. They actually like taking on risks. So if you think about placing a bet at a casino or with a sports book, most of those bets, they're not fair. In fact, they're negative expected value, but the people who like to gamble are still willing to place those bets because they get some enjoyment, they get some entertainment just from taking on risk. So I can say that most people are risk averse, but some people are risk loving. Now, when most people are faced with an uncertain prospect, we might imagine that they would just pick the option that had the highest expected value, the one that gave them the highest payoff on average. But we have a famous example that's called the St. Petersburg paradox that shows that this isn't always the case. And this paradox also helps to illustrate how our understanding of risk attitudes developed. So let's imagine that you're being offered a bet where you keep flipping a coin as long as it comes up tails, okay? So if you flip a coin and it ends up heads, then you cash out with a payoff of 2, but with a tails, you flip again, and the pot is doubled. So if you get tails and then heads, you get 4, you get 2 tails, you flip again, and so you get 8 here, 16 here, and so on down, okay? Each coin flip is going to be an independent event with probability 1/2 for heads or tails. So if we look at all the possible outcomes, the probability of getting a payoff of 2 is going to be 1/2 because it requires us to get a heads on the first flip. In order to get $4, we need to get a tails and then a heads. So the probability of that is 1/2 times 1/2 or 1/4. The probability of getting $8 is 1/8. The probability of getting $16 is 1/16, and so on. So if we're trying to calculate the expected value of this gamble, well, we would take $2 times 1/2 plus $4 times 1/4 plus $8 times 1/8 plus $16 times 1/16, and so on. So we get 1 plus 1 plus 1 plus 1 all the way up to infinity. Because this game could potentially go on for a really long time if we flip tails. And every time we flip tails, the pot's just getting bigger and bigger and bigger. If you were just seeking to maximize your expected payoff, well, because the expected value of this gamble is infinite, you would be willing to pay any amount of money to play this game, right? Because you're getting, on average, infinite money. So however much it costs, you would be willing to pay. However, if we look at what's going on a little bit more closely, we quickly realize that that's not really that good of a deal, right? Because half of the time, your first flip is a head. So half of the time, you end up with only $2. And in fact, you only have a 1 in 8 chance of getting more than $10. So if the entry fee to play this game were $10, you would only have a 1 in 8 chance of making a profit. So why is the expected value infinite? Well, the expected value is infinite because there's a very small chance that you could flip 10, 50, 100 tails in a row before you flip your first heads. And in those cases, your payoff would be extremely high, even though the probability would be very small. But you can see that each of these terms is contributing 1 to the expected value. So this term contributes the same amount to the expected value as the term where you get 150 tails in a row before you flip your first heads. Now, if we were to think about what does it even mean to flip tails 200 times in a row and then get a heads? Well, we would get paid 2 to the $200, which is a lot of money, more than we could possibly ever spend. And the probability is basically 0. So when we're thinking about this term contributing the same to the expected value as this term, the much more likely outcome that we flip heads on the first flip and just get $2, well, clearly we're not thinking about these two possibilities in the same way. Ultimately, the value of money is going to come from what it's able to buy. And if there's a diminishing marginal utility of consumption, which we saw when we were studying consumer theory, then there's going to be a diminishing marginal utility of wealth as well. So getting $1,000 is definitely better than getting $100, but it isn't quite 10 times better. And the higher the payoff is, the more that the marginal value is going to drop off. So rather than maximizing their expected payoff, we're going to think about people maximizing their expected utility. So pi I is going to be the probability of xi, and I'm going to maximize the expected value of this utility function. If the utility function is concave, which means that we have diminishing marginal utility for wealth, then we're going to have individuals who exhibit aversion to risk. Let's say we have a utility function, log x. If we use this function to calculate the expected utility in the St. Petersburg game, we would get 1/2 times log of 2 plus 1/4 times log of 4, and so on. And if we were to sum all of these up, this would sum to about 1.39. Now, just like with any other utility number, an expected utility of 1.39 doesn't tell me a whole lot because the utility is just a number. We can better interpret this by realizing that 1.39 is equal to the log of 4. What that means is that from the expected utility calculation, the expected utility you would get from taking this gamble is the same as the utility of just being given $4 for certain. And that means that $4 is a much more reasonable assessment of what somebody would pay in order to play this game, rather than the near infinite amount we found when we were just doing expected value. The canonical theory of expected utility was described by von Neumann and Morgenstern, and it states that under certain assumptions, an individual's preferences over random bets can be represented by an expected utility function, which we can construct this way. So we're going to have a number of outcomes, and we're going to arrange them in increasing order of desirability. So x1 is going to be the worst outcome. We're going to assign the worst outcome a utility of 0. xn is going to be the best outcome. We're going to assign a utility of 1. Then, for all of the outcomes between the best and worst, we're going to find that utility by using the following procedure. We're going to take one of these middle outcomes, xi, and compare that against a random prospect, where with probability pi I, we get the best outcome, and with probability 1 minus pi I, we get the worst outcome. Now we can see that if pi I is high enough, if there's a high enough probability of getting the best outcome, I'm going to prefer the gamble to getting xi. Conversely, if pi I is low enough, I would rather take xi because if I take the gamble, I'm more than likely going to get x1. So what that means is that there should be some value of pi I where I'm exactly indifferent between these two prospects. For this value of pi I, I'm exactly indifferent between getting xi for certain and getting a lottery where I get xm with probability pi I and x1 with probability 1 minus pi I. So written in utility terms, the utility of xi equals the expected utility of this gamble, which is pi I times u of xn plus 1 minus pi I times u of x1. But if you look up here, we fixed u of xn to equal 1 and u of x1 to equal 0. So this whole thing is just going to be equal to pi I. So we're going to assign this probability as the utility of xi. What we can then do is we're going to do this procedure for each outcome from x2 to xn minus 1, and that's going to give us a utility value for each outcome that x can take. By the von Neumann-Morgenstern theorem, once we have the utilities for each of the xi's, then we can compare any pair of lotteries just by comparing the expected utility. So let's say that gamble A is going to give me x2 with probability A and x3 with probability 1 minus A. And then gamble B is going to give me x4 with probability B and x5 with probability 1 minus B. Well, the expected utility of A is just going to be A times the utility of x2, which is pi 2, plus 1 minus A times pi 3. The expected utility of B is going to be B times pi 4, plus 1 minus B times pi 5. If, as in this case, we have that the expected utility of A is higher than the expected utility of B, that means that if we're presented with these two options, I'm going to choose A over B. If we have concave utility functions, then we're going to have decision makers that exhibit risk-averse behavior. So we often can take the variance of a random bet as a measure of how risky it is, but actually this is not the only property that matters. And there's many examples of gambles with the same mean and variance that are still approached differently. However, just to get us thinking about the problem in the right way, we can imagine that there's going to be a trade-off between expected payoff and variance. So if you're willing to absorb some risk, you can get a higher return on average. If we have a diminishing marginal utility of wealth, then a potential loss is going to be more impactful than a gain of equal size. So most people would not be willing to bet $1,000 on a coin flip because the possibility of losing $1,000 is going to hurt much more than the possibility of gaining $1,000 would help you. In order to quantify risk aversion, let's say that W naught is your initial wealth and U is a von Neumann-Morgenstern utility function. And let's say gamble A is going to be a 50-50 coin flip for H dollars, so plus H minus H here. So the expected utility of A is going to be 1/2 times U of W naught plus H plus 1/2 U of W naught minus H. Now, if U is a concave function, then the gain will not be felt as much as the loss. So this expected utility is going to be lower than the utility of just your starting wealth. So if you're worse off taking the gamble than not taking it. If I look at gamble B is just gamble A, but doubled in size. Now, if I have, again, a concave utility, gamble B is going to be even worse than gamble A because I'm potentially losing twice as much. The fact that I'm potentially gaining twice as much doesn't matter as much to me. This graph shows why a concave utility function leads to risk-averse behavior. Starting at the initial wealth of W naught, we can find the utility of not taking the gamble, as well as the utilities of winning H or losing H. If we have a 50-50 bet, then the expected utility will be halfway between U of W naught plus H and U of W naught minus H, which we can find by drawing the line connecting these 2 points. Since U is a concave function, this line is always going to lie below the graph. That means the utility of the expected value is higher than the expected value of the utility. What that means is that an individual with a concave utility function will always decline a bet if there is an option to receive the mean value for certain. Indeed, this preference for certainty means that you will be willing to give up some money in order to avoid taking risks. And we can show this by finding the level of wealth that gives the same utility as the expected utility of the gamble. That's going to be called the certainty equivalent, or CE, of A. With a concave function, the certainty equivalent will always be less than the expected value, which indicates that you're willing to give up some money in order to avoid the gamble. If we now plot gamble B on the same graph, we can see that doubling the size of the bet makes the utility of winning slightly better, but makes the utility of losing much worse. So that the expected utility of B is even less than the expected utility of A. So correspondingly, the certainty equivalent of B is also less than the certainty equivalent of A. For a risk-averse individual, the certainty equivalent of a bet is always lower than the expected value, meaning that they're willing to pay something in order to avoid taking on risk. This idea, of course, is what led to the development of various forms of insurance that serve exactly this need. So let's imagine we have someone who has a starting wealth of $100,000, and they have a 25% chance, so probability 1/4, of crashing their car, which is worth $20,000. So potential loss of $20,000. If I have log utility, then without insurance, I would have a 3/4 chance of getting log 100,000 and a 1/4 chance of having a total wealth of 80,000. So this gives me an expected utility of about 11.457. Once again, this number doesn't have that much meaning on its own, so we should interpret it by looking at certainty equivalence. A fair insurance policy is a policy where the probability of suffering the loss is exactly equal to the price of insurance. So here I have a potential loss of 20,000 and a probability of 1/4, meaning that the fair insurance premium is 5,000. if I buy $20,000 worth of insurance for $5,000, that means that my final wealth will be $95,000 whether I crash my car or not. That's approximately equal to 11.462. So I'm better off with insurance than without it. However, because the expected utility is higher under fair insurance than with no insurance at all, the insurance company, if it were not forced to charge fair insurance, could actually charge a little bit more than this, right? In order to figure out what's the highest premium that the insurance company could charge, we want to find the certainty equivalent. So the certainty equivalent in this case, U of 100,000 minus X, we set this utility equal to the expected utility of no insurance. And we get that X is about 5,426. What this indicates is that people are willing to pay this much for insurance, which gives a profit of 426 to the insurance company. So people are willing to pay an additional premium to avoid risk, which allows the insurance company to make a profit. Knowing that concave utility functions are going to translate to risk-averse behavior, we can quantify risk aversion by measuring the curvature of the utility function. So this is called the coefficient of absolute risk aversion. The coefficient of absolute risk aversion is given by minus U double prime over U prime. To understand how we can derive the risk aversion measure, let's try doing a Taylor series expansion of both sides of this equation. For the right-hand side, we only need the linear approximation. So that's going to be U of W minus P times U prime of W plus other terms, which we don't need. On the left-hand side, we're going to need some additional terms, though, because the Taylor series expansion of this is going to be U of W plus the expected value of H times U prime of W. But because it's a fair bet, the expected value of H is 0, so that whole term drops off, plus the expected value of H squared over 2 times U double prime of W. If we set these two expressions equal to each other, we just get that this term has to equal this term. And if we let this whole thing just equal K, we're going to have that P is equal to minus K U double prime of W over U prime of W, or K times the coefficient of absolute risk aversion. So what we can see is that P, which is the amount that you would be willing to pay to avoid the bet, depends on K, which measures the variance of the bet, times RW, which is your coefficient of risk aversion. So how much risk is there and how much do I not want the risk? It's often taken as given that as you become wealthier, you can more easily afford to take on risk, and so you become less averse to gambles that you would have avoided before. So it is true that the impact of losses is reduced at higher levels of wealth if you have diminishing marginal utility, but the same is also going to be true of gains, right? Losing a bet feels less significant, but winning also feels less significant if your starting wealth is higher. So ultimately, the relationship between wealth and risk aversion is going to depend on the exact shape of the utility function. With a quadratic utility like this, the coefficient of absolute risk aversion, U prime, is B plus 2CW, and U double prime is just 2C. So what we can see is that if B is positive and C is negative, then the coefficient of absolute risk aversion will increase with wealth. If I have log utility, then the coefficient of absolute risk aversion is going to be 1 over W for U prime minus 1 over W squared for U double prime. So this whole thing will just be 1 over W. Here, the coefficient of risk aversion will decrease as my wealth increases. Finally, we have a special case where, let's say U of W is minus E to the minus AW. So this is known as the constant absolute risk aversion, or Cara utility. The reason for this is if I compute the absolute risk aversion, in the denominator, I'm going to get this. In the numerator, I'm going to get this. This all cancels out and gives me a coefficient of A. So if I had an individual with Cara utility, their attitude toward risk would be the same no matter what wealth level they're at. So let's say that we had someone with Cara utility and they were presented with a coin flip of winning 1,000 or losing 1,000, and we want to find how much they're willing to pay to avoid this. So we want to compute the certainty equivalent. So U of W is minus E to the minus AW. So we want the utility of losing F for certain to equal the expected utility, so probably 1/2 of gaining 1,000 plus 1/2 times the utility of losing 1,000. Now, what we can see here is that we can multiply both sides by e to the AW naught. That's going to cancel out this term, and this term, and this term. Or we're just going to be left with e to the AF is equal to 1/2 e to the minus 1,000A plus 1/2 e to the 1,000A. So the amount that we're willing to pay to avoid this bet doesn't depend on our starting wealth at all, which is what we would expect if we had constant absolute risk aversion. If we have a constant absolute risk aversion utility, so something like this, then that's not exactly the most plausible functional form, since we do have plenty of evidence that wealthier individuals are more willing to take on risks. However, the reason that we use this utility form a lot is because it plays pretty nicely with the Gaussian PDF. So let's say that wealth is normally distributed with mean mu and variance sigma squared. Then it's going to have the density function f of w, which is given by this thing. So minus mu squared over 2 sigma squared. If I want to compute the expected utility of w, well, that's looking a little complicated, but I can do a change of variable to simplify this a little bit. So I'm going to let z equal w minus mu over sigma. So what I'm doing is I'm subtracting the mean, dividing by the standard deviation, and this is going to give me a standard normal random variable. So it's going to have a mean 0 and variance 1. So the expected utility is I'm integrating the utility across the density function f of w. So that's going to equal minus 1 over square root of 2 pi sigma squared. That comes out because there's no w in there. And then I'm going to have minus e to the minus aw. So that's going to be e to the minus aw. W is sigma z plus mu times this thing. Well, this thing is just going to be e to the minus z squared over 2, all that dz. Now let's think about what happens when we multiply these two terms. Well, multiplying these two terms just means we add the exponents. So let's see what happens there. We're going to do e to the minus 1/2 times, we have z squared here. We're going to have plus 2a sigma z here. And what we're going to do is we're going to complete the square. So if we complete the square, that's going to give us a squared sigma squared. So all of this is equal to z plus a sigma squared. But because we added this term, we have to subtract this term as well. And then finally, we have the last term from here to deal with. So that's going to be plus 2a times mu, and all this dz. What we can do now is we can pull out these two terms. So that's going to give us minus e to the minus a times mu minus a sigma squared over 2 times the remainder. So I have this term in front again, and I'm integrating e to the minus z plus a sigma squared over 2 dz. If we follow the change of variable we had before, z plus a sigma is equal to w minus mu minus a sigma squared over sigma. And that's going to be another normally distributed random variable. At any time I integrate the density of a normally distributed random variable across its entire support from minus infinity to infinity, that's always going to integrate to 1. So this whole term integrates to 1, and so the expected utility is just all this stuff that's left over. What that means is that this is going to be equal to my certainty equivalent, or written out, the certainty equivalent of this random wealth is equal to the expected value of w minus a over 2 times the variance of w. So this second term, therefore, represents the premium that I'm willing to pay to avoid risk. And what we can see is that with constant absolute risk aversion, the premium I'm willing to pay depends on how much risk I face, so the variance of w, as well as my coefficient of absolute risk aversion, which is a. Thinking in absolute terms, we would expect wealthier people to be less risk averse in the sense that they'd be more willing to take on a bet of a fixed size. So after all, betting $1,000 on a coin flip might be a big deal for someone like you or me, but for someone like Elon Musk, well, if he were to take on the same bet, the impact would barely even be a rounding error. So it wouldn't actually be that meaningful to say that he's more of a risk taker, because that's a decision that an average person would agonize over, but would be utterly inconsequential for him. So rather than thinking about bets of a fixed amount, let's instead consider gambles where an individual has to risk a proportion of their overall wealth. In this case, the intuition is going to flip rather dramatically, since for a typical person with little or no net worth, risking 1% of their wealth means pretty much nothing. But for a wealthy billionaire, that same bet would be far more significant. We can measure the coefficient of relative risk aversion by multiplying the absolute coefficient by W. So it's minus W times the second derivative over the first derivative. If we have a power utility function, so U of W is W to the R over R. As long as R is not zero, actually, log utility is a special case of power utility when R is equal to zero. Well, we're going to have that U prime is W to the R minus 1, and U double prime is R minus 1 times W to the R minus 2, so that the coefficient of absolute risk aversion is going to equal 1 minus R over W. So this utility function is going to exhibit decreasing absolute risk aversion. But the coefficient of relative risk aversion is just this multiplied by W, or 1 minus R. That means that this is a constant relative risk aversion utility. So the log utility that we kind of default to for all of our examples actually has a special property where I'm going to exhibit the same attitude toward risking a fixed proportion of my wealth. With relative risk aversion, we can ask the same question we asked before: how much you're willing to give up to avoid a particular gamble. Except in this case, both of these are expressed as a fraction of your wealth. So let's imagine that we have another 50-50 bet, except instead of being for a fixed amount, it's going to be for 10% of our starting wealth. So once again, we can calculate the certainty equivalent. So let's say that we have log utility. So log utility is a special case of constant relative risk aversion. Then we want to set the log of the certainty equivalent 1 minus F times W naught equal to the expected utility. So 1/2 log of 1.1 W plus 1/2 log of 0.9 W. So F is the fraction of your wealth that you're willing to give up to avoid having to take this bet. What we can see here is if we subtract log of W naught from both sides, we can eliminate the starting wealth from the calculation. So this is equal to 1/2 log of 0.99. And this gives us F of about 0.005. So what that's saying is that you're willing to give up about 0.5% of your wealth to avoid having to take this gamble where you're flipping a coin for 10% of your wealth. As you might expect, questions of risk and uncertainty loom large in all spheres of economic analysis, and much energy has been devoted to coming up with ways to deal with risk and mitigate its effects. Individuals or firms can buy insurance against the risks they face, effectively transferring it to another entity who is presumably better equipped to deal with it. They can also diversify their investment portfolios so that the risks of the individual components will cancel each other out without harming the overall expected return. They can retain some form of flexibility in their decisions, allowing them to alter their course of action after realizing the outcome of some random event. And finally, they can gather information to reduce the amount of uncertainty that they're going to face. We're going to go over each of these one by one. When it comes to insurance pricing, an insurer that offers fair insurance will inevitably fail because they'll be paying out all the money they receive in claims, and therefore aren't going to be able to cover their own overhead costs. However, since insurees are typically presumed to be risk averse, they'll be willing to pay some higher premium than the fair rate in order to avoid taking on risks. There's a number of factors that significantly complicate the issue of insurance pricing. For one, insurance policies typically rely on pooling large numbers of insurees, taking advantage of the law of large numbers to make sure that the actual incidence of loss is going to closely match the estimated probability. However, this relies on the events being insured against to actually be independent. So with things like natural disasters, so like floods or earthquakes, many people will suffer losses at the same time, which renders the insurers unable to cover the damage unless they set their premiums to be prohibitively high. With certain rare or unpredictable so-called black swan events, there may be no precedent with which to estimate the probability of loss, or even an awareness that such a thing is possible until after the fact. So that makes it nearly impossible to insure against them. Even for relatively common forms of insurance like health or car insurance, we can have issues of informational asymmetry, which can be from hidden characteristics resulting in the adverse selection problem or hidden actions resulting in the moral hazard problem. For example, an auto insurance company faces a diverse pool of insurees that have different probabilities of getting into accidents. So depending on how they price their policies, they may only attract the bad drivers, leaving the good ones uninsured. Furthermore, a driver may behave differently if they know they're insured, possibly driving more recklessly, which increases the probability of accidents. If you were to ask any financial advisor for investing advice, the first thing they'd probably tell you is to diversify your portfolio. So don't put all your eggs in one basket. The reason for this is that if you have two risky assets, both are going to fluctuate in value, but it's unlikely that both of them will always move together, which means that the overall portfolio risk will be less than that of each asset individually. So let's say we have two assets and they're going to have the same mean as well as the same variance. We're going to have a diversified portfolio where a proportion alpha 1 of my wealth goes into stock 1 and 1 minus alpha 1 goes into stock 2. Then the mean return is just going to be the weighted average of the individual stock means. And because they have the same mean, the mean return of the diversified portfolio will be the same as if I were to invest in either stock individually. However, if I look at the variance of the diversified portfolio, that's going to be alpha 1 squared sigma 1 squared plus 1 minus alpha 1 squared times sigma 2 squared plus this term. Now, if I assume that these stocks move independently, so they have zero covariance, this third term will drop out. That's going to give us 1 minus 2 alpha 1 plus 2 alpha 1 squared times sigma 1 squared. And if we want to minimize the portfolio variance, that's going to be minimized at alpha 1 equals 1/2, which is going to give us a portfolio variance of only half of what the individual stock variances are. So if we split our wealth 50-50 between stock 1 and stock 2, the diversified portfolio is only going to have half the variance of each stock individually. So far, we've talked about various ways of dealing with risks that presume that your actions will be fixed regardless of what the resolution of the uncertain event is. However, you can give yourself greater flexibility by giving yourself options, choosing a course of action that allows you to defer an important decision until down the line when the uncertainty in some future event is realized. Options in finance are derivatives that give the holder a right to buy or sell some asset in the future at a predetermined price, which is known as the strike price. If you hold call options on a stock with a strike price of 100, then if the stock price exceeds 100 when the options mature, you're going to exercise them at a gain. But then if the stock price ends up below 100, you can just decline the option and avoid suffering a loss. Certain actions outside of financial context can also give us the same kind of flexibility of actions that an options contract would. To model a real option, let's suppose there's some uncertain event X, and then there's N different choices that you can make, each with a different payoff function. So OI is the payoff function for choice I, which depends on the resolution of the uncertainty X. Without any flexibility, you would just have to accept the uncertain nature of X and choose whichever option gave the highest expected utility. So you want to maximize the expected utility over all of your possible choices. However, with flexibility, you can choose the correct action after the fact. So whatever X is, you choose the course of action that maximizes your utility, and then you take the expected value over that. Now, you're not removing the source of the uncertainty. So the fact that X is random is still going to affect your outcome. However, it is going to improve the result that you get. In this diagram, the choice O1 is going to pay off well when X is low, while O2 pays off well when X is high. So the payoffs are shown on the left graph, and the utilities for a risk-averse individual are shown on the right graph. If you had an option to pick your action after observing X, then you would choose O1 when X is low and O2 when X is high. So your utility function would be the upper envelope of the two lines. This is always going to be an improvement over having to commit to either O1 or O2 ahead of time. Generally speaking, it's usually better to have more options, although in certain strategic contexts, it might actually be better to limit your choices. For example, it might not seem like a good idea to sign a contract that binds you to some kind of commitment, even in unfavorable circumstances. However, doing so can signal to the other party that you're trustworthy. And if you don't send this signal, they may not want to deal with you at all. However, we're not going to deal with these sorts of problems in this chapter. In general, having flexibility is valuable enough that individuals are usually willing to pay a price in order to retain this option. This diagram shows the effect of adding a third option. On the left, O3 is the best choice for at least some values of X. And so having this additional alternative is better than not having it. On the right, O3 is never the best choice, and so it doesn't add any additional value. However, it's also not going to make you any worse off just by being there. As an example, let's consider having a flexible fuel car that can run either on fossil fuels or biofuels. So the value of fossil fuel cars relies on network effects, right? Having a large number of cars that run on fossil fuels is going to drive the production of these fuels. And in turn, the availability of fuel is going to make cars that run on them more attractive. So therefore, the value of any kind of car depends on the relative importance in the future of the fuel that it runs on. And that's going to be the relevant uncertainty here. Let's let X be the relative importance of biofuels in the future. And let's say that this is uniformly distributed between 0 and 1. So the payoff to a fossil fuel car is going to be 1 minus x, while the payoff to a biofuel car is going to be just x. If we want to calculate the expected payoff to buying a fossil fuel car, we're going to integrate this. The density function for a uniform distribution is just 1. So the integral of 1 minus x dx, that's going to be x minus x squared over 2 from 0 to 1, or just 1/2. Likewise, the expected value of owning a biofuel car, we're going to integrate x from 0 to 1. That's going to be x squared over 2 from 0 to 1. That's also going to be 1/2. Now, let's think about the payoff to owning a flexible fuel car, which you can fill up with fossil fuels if those are more prevalent, or with biofuels if those end up taking over. So you're going to receive the maximum of O1 or O2 regardless of x. So if I want to calculate the expected value of that, I would integrate the maximum of 1 minus x, or x, over the density. What that means is if x is less than 1/2, I would choose to fill it up with fossil fuels. If x is greater than 1/2, I would choose to fill it up with biofuels. That's going to give me x minus x squared over 2 from 0 to 1/2, plus x squared over 2 from 1/2 to 1. Doing all that summing, we get a total expected value of 3/4. So having a flexible fuel car is better than having either a car that runs only on biofuels or a car that only runs on fossil fuels. Now let's assume that the individual is risk averse. Let's say their utility is equal to the square root of their outcome. Then the expected utility to owning a fossil fuel car, I'm going to integrate the square root of 1 minus x dx. That's going to be minus 2/3 1 minus x to the 3/2, evaluated from 0 to 1, or 2/3. And likewise, the expected utility of a biofuel car is going to be integrating square root of x from 0 to 1. And that's likewise going to be 2/3. If I have a flexible fuel car, once again, I'm going to choose to fill it up with fossil fuels if x is less than 1/2, and fill it up with biofuels if x is greater than 1/2. But let's imagine that I have to pay an additional premium in order to get this flexibility. So it's going to be the maximum of u of O1 minus f and u of O2 minus f. So that's going to be from 0 to 1/2, it's going to be the square root of 1 minus x minus f dx, plus from 1/2 to 1, the square root of x minus f dx. We can see on this graph that while the expected utility of a single fuel car is fixed at 2/3, the expected utility to a flexible fuel car is a decreasing function of the premium f that we have to pay for the flexibility, which crosses at a price of about 0.3. So that's going to define the maximum price that a consumer is willing to pay for flexibility. Real options show that there can sometimes be value in delaying an action until the resolution of some future uncertainty, as you'll be better off making the right decision rather than prematurely committing to a potentially wrong course of action. As these options usually come with a cost though, you have to weigh whether the potential benefits are enough to justify paying the cost to retain flexibility, accounting both for your own risk preferences and the value of delaying your choice. The concepts of uncertainty and information are very closely related, as often something only appears uncertain because you just don't have enough information, and it might be possible to acquire some relevant information at a cost, whether that be the cost of doing some research or just outright paying someone else for it. In that sense, information is a commodity like anything else, though crucially, it's a public good, in that it's both non-rival and non-exclusive. And these are concepts that we'll see later on. What that means is that when you share information with someone else, you don't lose access to it yourself. And that once the information gets out, you can't prevent other people from accessing it. We can see that the fee that you'd be willing to pay for information exactly mirrors the fee that you'd be willing to pay for a real option. The only difference is whether the uncertain event has yet to be resolved or has already been resolved, just that you don't know what the outcome is. And from your perspective, those are exactly the same thing. So far, we've been dealing with risk and uncertainty in terms of probabilities, but it's more informative sometimes to associate random events with states of the world. So rather than saying that there's a 50-50 chance that the world will be good or bad, we can divide the future into two states, one representing good times and one representing bad times, and then assign a probability to each state. With these states defined, we can define contingent commodities. So those are commodities whose payoff depends on what the state of the world is. So for example, let's say I have an asset that paid $1 but only in the good state, and then another asset that paid the same $1 only in the bad state. Now, both of these could be described as paying $1 with probability 1/2, since like we said, both states are equally likely. However, these are qualitatively different things, so it's unlikely that they're going to be equally valuable. Let's let the state of the world be either good or bad. And the probability of the bad state is given by pi. The individual is going to maximize the expected utility of wealth, which is going to be 1 minus pi times u of wg plus pi times u of wb. So let's suppose that there are contingent goods for the good and bad state that are going to grant 1 unit of wealth in the corresponding state. So for a price of PG, you can buy an asset that will pay you $1 only in the good state, and at a price of PB, you can buy an asset that will give you $1 but only in the bad state. The individual then has to decide how to divide their starting wealth between these two assets. That's going to give us the budget constraint. W naught is equal to PG WG plus PB WB. So you are starting off with wealth W naught, and you're buying WG units of the good state asset and WB units of the bad state asset, meaning that your payoff in the good state will be WG, your payoff in the bad state will be WB. The price ratio, PG over PB, that's going to be the rate at which I can trade wealth in one state for wealth in the other state. If the markets are well developed, then the price of each contingent claim should equal the probability of that state actually happening. So PG should be 1 minus pi, and PB should be equal to pi. Maximizing this expected utility, we're going to get a familiar result, which is that the ratio of the marginal utilities in each state is going to equal the price ratio. And if the prices are fair, so PG is 1 minus pi, PB is equal to pi, then these will cancel out, which says that the ratio of marginal utilities U prime of WG over U prime of WB is equal to 1. And if U is a concave function, I have U prime of WG equals U prime of WB, which means that WG equals WB. What that means is that if the contingent claims markets are actuarially fair, then a risk-averse individual is going to choose to buy contingent claims such that their wealth will be the same in both states. What that means intuitively is that if prices are fair, then you can freely shift wealth between the good state and the bad state while preserving the same expected value. So if you're risk averse and you can reduce risk without changing your expected value, you're going to do that until you no longer have any risk, which is going to give you the highest expected utility if you're risk averse. This diagram shows the state preference model where the axes represent wealth in the two states. The budget line is actuarially fair so that its slope minus PG over PB is equal to minus 1 minus pi over pi. And so the individual will be best off along the certainty line where the wealth is the same in both states. The budget line I prime is flatter, indicating that PB is relatively higher, as the markets might expect people to be more willing to pay to make up for shortfalls in the bad states rather than to gain even more wealth when times are already good. In this case, the optimum is going to have WG greater than WB, indicating that this individual doesn't find it worthwhile to eliminate all risk at those prices. Let's say we have an individual with a starting wealth of 100,000 who has a probability 1/4 chance of crashing their car, and the loss is equal to 20,000. With no insurance, you have a payoff of 100,000 in the good state and 80,000 in the bad state. So if I have log utility, the no insurance expected utility is 3/4 log of 100,000 plus 1/4 log of 80,000, or about 11.457. When we write the budget constraint, we can imagine that this individual holds 100,000 shares of the good asset and 80,000 shares of the bad asset, so that they begin with wealth equal to PG times 100,000 plus PB times 80,000. Then they can reallocate their wealth between the good asset and the bad asset any way they like. Their final asset holdings are equal in value to their initial asset holdings. If the prices are actuarially fair, then their starting wealth and therefore their final wealth should be equal to 95,000. The utility of the average wealth of 95,000 is about 11.462, which is higher than the expected utility of no insurance. So individuals will prefer to be on the certainty line if they can. In order to do this, they're going to sell 5,000 shares of the good asset and buy 15,000 shares of the bad asset. And so delta WB over delta WG is going to equal -3, which not coincidentally is also equal to -1 minus pi over pi, so the odds ratio. However, from the perspective of the insurance company, full insurance isn't always a good thing because this raises a potential moral hazard problem. So a driver that's fully insured against all damages is going to have less of an incentive to drive carefully and could potentially raise the odds of getting into an accident. One solution that's used by insurers is to offer a plan with a deductible. So, for example, let's imagine that the plan doesn't cover the first $1,000 of the loss, and the plan is priced at $4,900. That's going to give us a wealth in the good state of 95.1 and a wealth in the bad state. So the plan only covers 19,000 of the loss as opposed to 20,000. The wealth in the bad state will be 94.1. So this insurance plan doesn't fully remove the risk. The wealth will be higher in the good state than the bad state. However, if I compute the expected utility of this, that's about 11.460. That's not as good as having full insurance at fair prices, but it's still better than having no insurance. So if this were the only alternative, the driver would happily buy it. Insurance markets are composed of diverse individuals with various risk attitudes. We might be able to measure that by looking at the coefficient of relative risk aversion, R. The more highly negative that R is, the more risk averse, and thus the more sharply curved the indifference curves are. This diagram shows the indifference curves for a pair of individuals where U1 is more risk averse than U2. Therefore, when faced with the same loss of H in the bad state, individual 1 is going to require more compensation in the good state to stay at the same level of utility compared to individual 2. A heterogeneous pool of insurees is going to pose a problem for insurers because each of them has relevant characteristics that are private information. That creates an informational asymmetry. In general, these asymmetries create various problems, as in certain cases, individuals are going to seek to hide information from their counterparty, but in other cases, they will attempt to reveal the information but lack a mechanism for credibly doing so. Gathering information to close this gap can be very costly, and that can vary based on the capabilities and knowledge of the individual. We're going to return to study problems with asymmetric information more later on.